Hi everyone, we're just going to continue with series circuits, continue from where we left off last time. We're going to, before I jump into some new material, I just want to kind of go over another example just to make sure we have everything straight in our minds and straight in our, the ideas that we know about series circuits, right? So I'm going to purposely change the setup of the circuit just to show us that really it doesn't ultimately change anything in how we solve the problem, right? So notice I put the power supply or battery off on the right hand side rather than the usual left hand side of things. I know for a lot of you that's going to break your minds, but it really doesn't change anything. That's the whole purpose of this, is that the positions of all these things, resistors and power supplies, batteries, ultimately doesn't really matter in a series circuit. So we're going to have a 10 volt source, we're going to have a 100 ohm resistor here, 400 ohm, a 500 ohm, and a 1K resistor as well. So as we've mentioned before, first thing to do is to actually draw the ground, because I didn't draw ground. Okay, so here's our ground. So that's our 0 volts. And the next thing is to realize which direction is our current going in. So this is the positive and that's the negative, given by the small bar on the battery or power supply is the negative side. The long bar is the positive. That's by definition, all right? So we don't change it. It's always like this. And we say that the current flows out of the positive, okay? And will flow in a counterclockwise direction in this case. And I'm just overdoing it with the arrows just so that we realize that the current flows in a counterclockwise way. So that's the current I. We've also said that when a current flows through a resistor, it always flows from a higher potential to lower. So when we kind of label our resistors, we put a plus sign on this side of the resistor and a minus on this side to distinguish that as the current flows, this side is going to have a higher potential, a higher energy than this side. So an electron that passes through is going to have a lot less energy once it gets to the other side, right? We continue with the other resistors. It's the same thing, higher potential, lower potential, and it's always following the direction of the current. Current flows from higher potential to lower potential. And if we want to just label these resistors, I'm going to call this one R1, R2, R3, R4. We can then say that the potential difference across this resistor is VR1, just so that's labeled. So that's the voltage that is lost or is across the 100 ohm resistor. Same thing for R2. This is going to be VR2. This is the higher potential, lower potential, but the potential difference across the resistor is going to be VR2. And again, same thing for VR3 and VR4. Same idea. Now, having said that, we know that Ohm's law applies in all these situations. Ohm's law never changes. But before we go on, we also want to sort of define the R total. And we learned that the R total in a series circuit, and this is a series circuit, is all the resistors values added up. So we have R1 plus R2 plus R3 plus R4. And that's 100 ohms plus 400 ohms plus 500 ohms plus 1000 ohms, which when you add it up becomes 2000 ohms or 2 kilo ohms, right? And then further on, we know that Ohm's law is V equals IR. So we know V is 10, we don't know I, and we know R is 2 kilo ohms. So that means I will be 10 divided by 2 kilo ohms. And throw that into a quick calculator. And we get 0.005 amps or 5 milliamps. So that is our I. That's the current running through every single resistor through this circuit. Okay, that's the definition of a series circuit. So if we want to just maybe be a little clearer, okay, we can call this V total and R total, just so that we know it's referring to all the voltage and all the resistance. But because the current is the same everywhere, we can also do a little calculation to find every voltage drop across each resistor. So we know that VR1 will be equal to the current times R1. So that's 5 milliamps times 100 ohms, and that'll be 0.5 volts. VR2 is equal to I times R2. So 5 milliamps times 400 ohms equals, I'm just going to double check so I don't make a mistake. I'm pretty sure it should be 2. Yes, it is. Nothing worse than writing down a mistake and then realizing later that it was wrong. VR3 is I times R3. So again, 5 milliamps times 500. And that should be 2.5 volts. And VR4 equals I times R4. Oops, that looks like a subscript. I don't want that. I want it to look like times R4. So that's 5 milliamps times 1 kilo ohm, which is 5 volts. And to prove that we haven't made a mistake, the V total, which is equal to 10 volts, should also equal VR1 plus VR2 plus VR3 plus VR4. And 0.5 plus 2 plus 2.5 plus 5 does equal 10 volts. So we have not made a mistake here. And so that's just a quick sort of synopsis of what we talked about last class. Just double checking using Ohm's law and showing and proving that the total voltage and the total resistance gives us the current in the series circuit, which then we can use to calculate each voltage drop or each potential difference across every resistor. All right, so I'm going to stop this video here and click on the next one to watch the next part. All right.